All right, so organic chemistry is pretty different than what you guys covered in general chemistry. If you look at the periodic table, organic chemists only use a tiny, tiny portion of it. Particularly that top right-hand corner is where we look at. And prior to 1830, organic chemistry was something that wasn't really well understood. People talked about it a little bit, but it wasn't well defined. In fact, they used a little bit of superstition, and they said that organic compounds were things derived from vital forces. What exactly a vital force is, your guess is as good as mine, but there was some sort of spiritual aspect to it. They knew that organic compounds had to do with living matter most of the time. It wasn't super well understood. Does anybody know what the more modern definition of organic chemistry is?
Carbon.
Carbon, right? It's a whole branch of chemistry based on one element, right? So the modern definition is carbon-based chemistry. And that leads us to an important question, right? So the question is, why is carbon special? Does anybody have an answer?
It's everywhere.
It's everywhere? Okay, so it's abundant, we could say? Abundant. It can form 4 bonds. Carbon's really nice that way. It's pretty reliable, and it will usually form 4 bonds with a couple of exceptions, and we'll talk about that later. Does anybody have another reason why carbon's important?
Or carbon-based life forms.
Yep.
Or life can revolve around it.
So biomolecules, right? So how many of you guys have taken biology? So amino acids, nucleic acids, fats, proteins, you name it. It's got carbon in there, right? So most of the biomolecules in our body have carbon in it. It's very important if you're in the healthcare field. Yep.
You can get a lot of energy from combustion reactions.
Yeah. Is a good way to store energy. So if you think about gasoline in your car, that's stored energy in the form of carbon. If you think about sugar that you eat, that stored energy has carbon, right? So it's a great energy storage material. What about the bonds that carbon makes? What type of bonds does carbon really exclusively make?
Mostly sigma bonds.
Mostly sigma bonds? Covalent bonds? Yeah. So it forms covalent bonds. In particular, it forms pretty strong covalent bonds most of the time, which is why it's found in a lot of biomolecules. You don't want your biomolecules to fall apart. All right, so let's kind of move on a little bit. Carbon's really cool. We'll talk about it all year long, all of the cool reactions that you can do with it. But there's one guy I briefly wanted to introduce. Does anybody know who this person is? Give you a hint. His name's right above it.
Oh, is that Lewis?
Yep, Gilbert Lewis. So Gilbert Lewis is essentially the father of organic chemistry because he was the one who was the first person to describe a covalent bond. What is a covalent bond?
It's a non-polar bond between 2 nonmetals.
Okay, so it's something between 2 nonmetals. Sometimes covalent bonds could be polar, but essentially what it is it's a sharing of electrons. You guys remember that from Gen Chem? Ionic bonds, you transfer electrons. Covalent bonds, you share electrons. Sometimes not super evenly, sometimes very evenly. So he first described a covalent bond as a bond where 2 electrons are shared. And I always like his story because I know occasionally students, or professors for that matter, feel underappreciated. He was nominated for the Nobel Prize 38 times and ultimately did not win. Does anybody know another big field he's responsible for kind of pioneering? It also involves the word Lewis. Acids and bases, right? Lewis acids and bases. So he was the pioneer of organic chemistry, acid-base chemistry, really invented modern chemistry as we know it, but a lot of other chemists didn't like him. And so he constantly got kind of pushed to the side anytime the Nobel Prize was announced. It was kind of sad, and there's suspicion that he even committed suicide because of that, unfortunately. All right, so let's talk a little bit about valence electrons, and then we'll get into Lewis dot structures. One other thing, too, is particularly those of you in the back, if you can't see something I'm writing, raise your hand or go like this, motion for me to scroll up so that you can see. And if you can't hear me, you can also go like this, make a big circle with your hand. That way I'll repeat myself. All right, so review of valence electrons. What is a valence electron?
The most outer electrons on an atom.
Outermost electrons?
Most likely to react.
Most likely to react? I think those are all pretty good. Does anybody have another way of describing it? How can we really easily figure out how many valence electrons there are on an element?
It's the unfilled shell in the electron.
Yeah, it can be unfilled. There are some cases where it's kind of filled. If you look at noble gases, that's kind of the weird outlier. But the easiest way to determine how many valence electrons there are is right on top of the periodic table. You see 1A, 2A, 3A, 4A, 5A, 6A, 7A. That Roman numeral tells you exactly how many valence electrons are in that outermost or highest energy shell for that atom, right? So they are the outermost / highest energy electrons. All right, so let's do a couple examples. Hydrogen. How many valence electrons? One. Okay. So we do 1 dot, right? You guys remember that from Lewis dot structures? All right, what about carbon?
4.
4. So with Lewis dot structures, would I go 1, 2, 3, 4? Yeah, try to fill out each side first. Treat it like a square. You do 1, 2, 3, 4. And those are electrons that typically want to be paired either as a lone pair or bond somehow, right? Let's do another one. Boron.
7.
That's in group 3A, right? So 3 electrons. Boron's kind of an oddball that way. It doesn't follow the octet rule a lot of times because it only has 3 valence electrons. And like I said briefly, if we look at valence electrons, they tend to be paired. They can be paired as a lone pair, meaning they're kind of hanging out in open space, or they can be paired as a covalent bond. This is really important in organic chemistry. There are some situations where they are unpaired, but do you think that molecule is going to be very happy if it has unpaired electrons? No. So a lot of you guys spent some time out in the sun this summer. Have you guys heard of free radicals or sun damage? It's exactly what happens. Anytime you get unpaired electrons, your biomolecules start doing some crazy stuff, and that can cause all sorts of health problems. So radicals are the one exception where you don't have paired electrons, and they typically are quite unstable. All right, so let's review some Lewis dot structures. All right, so let's make a just really brief list of guidelines. I abbreviate electrons as E minus just to speed things up. Electrons tend to be paired. That's an important thing to remember anytime you're drawing a molecule as a Lewis dot structure. What's another important rule with Lewis dot structures? Octet rule, right? So atoms prefer to have 8 electrons around them. Occasionally they will have less or fewer electrons, but they will almost never have more than 8 electrons. Obviously, there are some weird exceptions, but the octet rule isn't a rule so much as a preference, right? So try to always have Lewis dot structures where you have 8 electrons around all of your atoms. You also want to include formal charge if needed. How can we determine the formal charge? Yeah.
If the atom of the element has more or less electrons.
Yeah, exactly. If we've got extra electrons, we're going to have a negative charge. If we've got a deficiency in electrons, we're going to have a positive charge. So the way I like to think of this is that charge can be found by taking your valence number, subtract your lone pair electrons, and then subtract 1/2 of your bonding. So let's take an example of this. I'm going to do a really simple one. Let's do HO minus. Hydroxide. You guys saw a lot of this when you did all your titration labs, right? Probably sick of hydroxide at this point. So we've got hydrogen. How many valence electrons? 1. Let me switch to black. This is kind of hard to see. So hydrogen has 1. Oxygen, how many does that have? 6. So we go 1, 2, 3, 4, 5, 6. We know that these are going to bond, right? We've got a covalent bond. However, what we're going to do is we're going to take an electron and dump it into this spot right there, right? So when we look at hydroxide, what we actually have is 1 extra electron around that oxygen, which means that we have to have a negative charge, right? So we have to use formal charges on the particular atom that has that charge, right? So if an extra electron is being thrown in, make it negative. If you're taking away an electron to follow all of your Lewis dot structure rules, it will be positive. All right, let's jump into some examples.
I've seen that as brackets before. Like you bracket and then you write like a negative at the top of the bracket. Is it other than like a block?
That's a good question. So occasionally, what you will see, let's take another example. Let's do NH4 plus. Nitrogen is going to be the central atom. Typically, your largest atom will be the central atom if carbon's not around. Nitrogen has how many valence electrons? 5. Okay, so let's draw a nitrogen there. Whoop, sorry. Sometimes my pen gets a little glitchy on me here. So nitrogen has 5. We know hydrogen has 1. So we'll go 1, 2, 3, 4, 5. We've got hydrogen over here. We've got hydrogen down here. We've got hydrogen over here. And we know we have to have a 4th hydrogen, which is right there. If we look at that nitrogen, it's got an extra electron, right? So what we're going to do is take this electron and pull it out from that nitrogen, right? So now we can pair up these two electrons, these two electrons, these two electrons, and these two electrons, which means that ammonia, or ammonium, excuse me, has 4 hydrogens, and then we can represent that with a positive charge. Occasionally, inorganic chemists in particular, instead of labeling the atom where the charge is on, they'll put a little bracket in the top right-hand corner and they'll do a plus sign like that. I really prefer in organic chemistry to label the particular atom where the charge is on. That way, if you've got a giant molecule, you can say, that nitrogen's positive or this oxygen's negative, as opposed to saying this molecule has a negative charge or a positive charge somewhere on it. Does that make sense? Okay, let's do a couple practice problems. And this will lead you into your pod as well. So let's do COCl2. Are there any history buffs in here? One? Just one? Oh, okay.
What does it take to be a buff?
But, I don't know. Do you like reading nerdy stuff? So this is phosgene gas. It was used in World War I as a poison weapon. Really nasty stuff. It's a little bit different than mustard gas, but if you inhale it, it'll essentially blister your lungs. Really awful chemical weapon. But let's try to figure out how to draw the Lewis dot structure for this. Remember, carbon likes to be in the middle of things. So carbon will most likely be the central atom here. I'll give you guys a minute to work on this. And then what I would do is check with your neighbor and then double check to make sure that you have correct formal charges if there are any formal charges. You guys are very quiet. You guys are welcome to talk to one another. Raise your hand if you feel pretty confident. A few people? All right, let's do this as a class really quick. So we know carbon likes to be in the center. How many valence electrons? 4. All right, so 1, 2, 3, 4. All right, let's do oxygen up here. How many valence electrons? 6. Okay, so we've got 1, 2, 3, 4, 5, 6. We've got chlorine and chlorine. How many valence electrons? 7. Okay, so 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Now let's circle the bonds here. We know chlorine just needs 1 electron to be paired, right? So it's probably going to bond with one of the unpaired electrons on carbon. Same with this chlorine. And then if we look at oxygen and carbon, well, we can pair that one. What about those remaining electrons between our oxygen and carbon?
Pi bond.
Pi bond, right? So in chemistry, we can have single, double, or triple bonds. So in this case, these extra electrons will bond up and form a pi bond. So if we look at phosgene gas, we can draw that as a double bond. Got 2 lone pairs coming off of that oxygen. Got chlorine down here, and then 3 lone pairs coming off of each of the chlorine atoms. So this would be the correct Lewis dot structure for phosgene gas. All right, I think we're going to leave it there today. I would encourage you to try to get started on the problem of the day tonight. If you're a little stuck, come talk to me, or go through your textbook or your old Gen Chem textbook and just kind of brush up on Lewis dot structures.
How do you spell that? Phos?
Yeah, or no. I'll have to look it up. I'm terrible with spelling.